Lesson 2.7 is going to be that variation problem. So for this lesson, you're going to need your textbook, and you're going to need no note cards this time, but just this video notes. We're going to review some ideas that you learned in Algebra 2, and then now we'll expand upon them with a new kind of scatter plot and a new kind of regression equation in addition to the other ones that we've already learned. Often in mathematics, we need to express relationships between quantities. One relationship that is frequently used in applied mathematics occurs when two quantities are proportional. The two variables x and y are proportional to each other or vary directly if their quotient is a constant. So we say y varies directly as x, or we use this equation y equals k times x. That should be familiar to you because you did a great big long unit about variation in Algebra 2, where k is the constant of proportionality or the constant of variation. So remember, k is that constant of variation. Y can also vary inversely as x, as in this situation, y equals k divided by x, or it may be represented by other relationships as described in different applications. You know these problems as four-step problems, those four-step problems that you learned to do in Algebra 2. For this lesson, we're going to examine inverse variation models. Okay, so example 1 says, force exerted by the electrical field between two charged objects is inversely proportional to the square of the distance between them. At a distance of 1.5 meters, you measure a force of 30 newtons. What will be the force at a distance of 3.0 meters? Use the four-step process that you learned in Algebra 2 to help you solve this problem. So, the first step is we're going to write our equation as a relationship. So we go back to this sentence, this first sentence of the problem, and this is how we're going to find our very general equation that we need to write. So it says the force exerted by the electrical field between two charged objects is, so there's equals, inversely proportional to the square of the distance between them. So force is inversely proportional, that's k over the square of the distance. So we write that equation first. The second step is we're going to substitute in the relationship that we know. We know that at a distance of 1.5 meters, so that would be 1.5, we have to square that in the denominator, the force would be 30 newtons. So we put 30 in for the force and 1.5 in for the distance. Okay? We want to solve that, so if we think of this as a proportion, we could cross multiply it, and we could get the value of k. So that would be 30 times 1.5 squared. So k is going to equal 67.5. Okay, the third step is now we're going to write a specific equation for this situation. Force will equal 67.5 divided by d squared. And then the last step is going to be what will be the force at a distance of 3 meters. So the force will equal 67.5 divided by 3 squared. So whatever 67.5 divided by 3 squared, 3 squared is 9, gives us, that would be a force of 7.5. And then we want to label it, and the force is in newtons, so we would say newtons. Alright? So if you remember those four-step problems, you'll see that this is not going to be anything different than what you've already done. If we want to change it to 15 meters, then we would use this specific equation. This is your specific equation, which is specific to this particular problem. It has the constant of proportionality for this problem. So I would just say force would equal 67.5 divided by 15 squared. So 67.5 divided by 15 squared gives us a force of 0.3 newtons. Okay, so 3/10 of a newton. All right, very good. All right, so what I want you to do is I want you to try example 2 by yourself and see if you can do all 4 steps just like we followed up above. So pause the video right now and see if you can do those 4 steps. And then when you put the video back on, I'll have my 4 steps shown for you. You can see if you can follow that and see if you got the same answer. Okay, as you can see, the intensity from the power source was inversely proportional to the square of the distance. So remember to square the distance. I got a K of 15,000. So my specific equation on part 3 was 15,000 over d squared. And then for part 4, I substituted in 10. I remembered to square it, and I came up with 150 lux. And for 23 centimeters, I got approximately 28.36 lux. Okay, if you think you're pretty sharp at doing those, then I think you'll find this next part something that you remember or something that you might be able to do. Okay, in the second column it says inverse variation is common to the physical world. According to Boyle's law, the volume of a gas varies inversely as the pressure. The pressure is measured in kilopascals and the volume is measured in milliliters. Okay? So example 3 says, in a chemistry lab you collect data on the pressure and volume of the gas, and the results are in this table below. Wants us to find a formula for relating the pressure and the volume of the gas sample that's studied in the lab. In other words, do 3 of the 4 steps. We want to come up with the specific equation for this. Now what you might remember from doing this last year is you would come down here and you would find a pair and you would examine this relationship. So to get from 20 to 40, you would multiply by 2. And so over here you would look at the relationship between these. So you'd have 253.3 divided by 120.9, the small one, 120.9. Okay, and we see that this relationship would from here to here would be that you would divide by, right, about 2.095. Okay. Now, if you wanted to pick another relationship to look at, we could do that too. We could say, okay, how about 40 to 80? To get from 40 to 80, you would multiply by 2 to get from 120 to 120.9 to 64.2. You would divide by about 1.883, so on. Okay, so remember, if we're multiplying on this side but we're dividing on this side, that's an inverse relationship. But these are 2, because I chose things that were times 2 over here. And this is approximately 2. This one's a little bigger, this one's a little smaller. So if we're multiplying by 2 here and dividing by about 2 over here, then that is an inverse relationship. It's not inversely as a square, it's just varying inversely. So to find our formula, what we would have to do is pick one of those relationships to look at. So we know that the pressure is going to vary inversely as the volume. And I think that was part of what was told up here. So what we can do is we can use any ordered pair. Okay? I don't know if you remember that from last year, but use any ordered pair. And so I'll just use the first ordered pair. I'll use 20 with 253.3. Okay? And so if I do that, then I say, well, 253.3 equals K over V, which is 20. And again, then I would cross multiply that, and I'd say my K value is equal to 5066. So 253.3 times 20 gives me that amount. Okay? So I'm saying my specific equation would be P is equal to 5066 over V. Okay? That's what I'm saying. My specific equation would look like. Okay, and it would approximate the things in the table. Well, what we want to do is get it a little more exact than that. So let's make a scatter plot of the data on our graphing calculator, and then let's just sketch what it looks like below. So you may need to pause the video to enter this data, and when you enter the data, you'll put the volume of the gases in list 1, and you can put the pressure in list 2. So go ahead and pause the data, or pause the video if you need to get that typed in. All right, I have my data typed in list 1 and 2. All right, and so I'm going to go up here to my y equals, turn this on, and make a scatter plot of that data. I'll just put it on a zoom 9 window. If I'm using my y equals, okay, get rid of that, and I'll just put this in a zoom 9 window. Okay, and so what I want to do is I want to look at this relationship by saying I have these dots that are doing this. Okay, it doesn't really look linear. It doesn't look like it could be quadratic because, you know, quadratic would have to go up as it goes to the right. We also did exponential. Exponential also looks like quadratic in the first quadrant. So this definitely looks like something that's an inverse square, because you might remember that, not inverse square, but an inverse is like this branch of a hyperbola. We wouldn't do anything with this branch down here. We'd just be looking at the branch in the first quadrant, since we're working with all positive data here. Okay, so this P equals K over V could also be written as P equals K V to the negative first power, because if that's a V to the first in the denominator and I bring that back up to the numerator, then I'm going to switch that sign around. I'm going to make it look like P equals K V to the negative first. So our calculator can actually calculate a model for us based on this, and it's something called a power regression. And it's called a power regression because it's in this form, y equals ab to the x, kind of like the form for the exponential function, but we're talking about this variable representing the negative first power. Okay? So if we do stat calculate, we want to come clear down here and we want to pick the power regression, which is letter A. So it's letter A on your list, and then you just need to tell it which two lists. So this one and this two, and it'll calculate us a power regression. All right, so you're going to notice that this power regression is going to be like an inverse situation for us. So if I substitute my A and my B in here, roughly I will have 4,947. I'll say 86, and then that's going to be times x to the negative 0.99887. That's what I'll put. All right. Now you're going to notice that this power right here is not exactly -1, and that's because we have some error involved. Not every one of these dots in our scatter plot is perfectly going to lie on that curve. In fact, I'm going to go ahead and put this in my y equals. And then let's graph it on there and let's just see. The points don't go exactly on the curve. Some of them are a little bit above and some of them are a little bit below. So there is some error or some residual to look at. But we're pretty darn close to having that to the negative first power. Not quite. Okay? Not quite x to the negative first power like you would see, or v to the negative first power in this particular case. All right? Well, the next thing it's going to ask us to do, over here on the back side, is to calculate the residuals for the model. So what it wants us really to do is go to our trace button here, take that first ordered pair, which is at 20 and then 253.3, and then go to our model and type in 20, and we get 248.2, and then write down how much difference there is. So we have 9 ordered pairs here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it wants us to find that. But I will tell you that there is an easier way to find that in your calculator. Okay? The calculator already knows where all the residuals are. And they're going to be stored under second stat, which is list. Okay, so I'm going to write that down. So it's second stat, which is the word list, second list. And then in my calculator, it's number 7. I don't know what it will be on your calculator. Some people's calculators, it might be 8 or 9. Some people might have it on number 4 or 5. But it should say RESID. RESID. That's the abbreviation for residual. So I'm going to go ahead and hit enter on that. Oops. Okay, hang on. Let's get out of this screen and let's be on a clear blank screen. Let's go second list, number 7, and then we want the residuals for what we just calculated, the last thing that was just calculated. So I'm going to hit enter, and it's going to give me these residuals. Okay? So I'm going to put some squiggly lines in front of this set that I'm going to make, and I'm going to approximate these residuals. So the first one's off by about 5.07. I'm going to scroll over, and I'm going to say the next one's off by approximately negative 5.07. Okay, so the third one has an error of negative 3.31. The fourth one has an error of about 2.20. The fifth one, the error is about 1.75. The sixth one is negative 0.12. 1, 2, 3, 4, 5, 6. The seventh one is 2.04. Then we have, there's a negative there, yes, negative 1.46. And the last one is at negative 0.44. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got all 9 of the residuals. So that's an easy, quick way if you want to get all of the residuals. All right? There are 4 possible residuals, or 4 positive residuals, and 4 negative residuals, aren't there? So there's 4 that are positive, 4 points that lie a little bit above the curve, and then there are 4 points that are going to lie a little bit below the curve, or 5 points. We're going to calculate the residuals for the model and then use them to assess the quality of the model. Okay, so here's what we're going to state. There are 4 positive residuals. So 4 times the error was positive, and 5 negative residuals. 5 times when we subtracted, the error would become negative. Okay, how about this? The residuals are not particularly large, are they? And maybe you want to say what they're relative to what. Are they large? Because we didn't put any scale up here on our graph. So we went back and looked at that graph. Let's look at the window for that graph. That graph starts at 12 and goes to 108. And then this first point is at 14.62 and goes up to 287.98. So in terms of the numbers in the graph being off by this residual amount, biggest and the smallest are positive and negative 5, just over 5, then the residuals are not large, relatively large, okay? And they do not show a pattern. Now, what's a pattern for residuals? A pattern for residuals would be that they might start out small, and every one you go to gets bigger and bigger and bigger, or less, 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 okay? These kind of vacillate back and forth between positive, negative, negative, positive, positive, negative, positive, negative, negative, okay? So that can tell you something, okay? But they do not show a pattern that would suggest a different model. we will work much more in lesson 2.8 on residuals. Okay? Now, once we have this model and we have it graphed, we can use it to make predictions. We want to know what volume would correspond to a pressure of 40. Okay, what would go with a pressure of 40? Well, we have to think about how we put the data in our calculator. Okay, the pressure is a Y value, I believe. Isn't it? Yep, the pressure is a Y value. So we're going to have to go in here and we're going to have to type in a Y value of 40. Now, if we check our window to see if that's going to work, yeah, that'd be okay. Oh, it doesn't quite meet up though, does it? Well, maybe it does and maybe it doesn't. I can't really tell. So I'm going to give myself some more room out here on my window. So I think I'll go out to 120. Give myself a little more room. Let that be graph. Okay, let's see if we can get it to intersect. Okay, it gives me this error message called no sign change error. What that's really telling me is within the window that I have, I don't have any sign change. In other words, I don't have any way to get it to intersect. Okay, so I'm going to go back to the drawing board here to the window, and I'm going to make the window even bigger because I do believe they're going to intersect there. So let me make it 150. All right, and I'll regraph it. Let's see what happens this time. Okay, clearly I can get it to intersect this time. Okay, and so when y is equal to 40, this is a y value, x is equal to 124.37385. Okay, and then my rule of thumb said that I could round to whatever the table does. The table rounds to the nearest tenth, so I would say I would put about 124.4. 124.4. Okay, and we would do mLs for that. What pressure corresponds to 75? Okay, well 75 is an x value, so I should be able to type in 70. Okay, stop right there. Get on 75, and I come up with about 66.3. About 66.3, and that would be those kilopascals. Okay? So there you go. You can use your model to make some really nice predictions, can't you? Okay. Problem number 4 is going to be another one that we're going to enter into our calculator. So I want you to pause the video. I want you to put these numbers. Let's put them in list 3 and list 4. So in case you have any trouble when you get to class, you'll still have the first 2 lists that you can ask me about. So let's put these in list 3 and list 4 and do exactly what it says. Make a scatter plot of the data and find a model for this. So pause the video and do that, and then I'll join you back here once you get that all entered into your calculator and you get your model made. As you can see, I have my scatter plot on here, and I have my curve that I fit to it using my power regression. My formula that I got was y is approximately 24,551.42, and then my x had a power of negative 0.8315402,197. You don't probably have all those decimal places written down, but what I want to point out to you is this is further away from our idea of getting x to the negative first power. This is not quite as strong as the other model, but you can see that the points lie a little bit further away. In fact, it asks us to come over here and to write down the residuals. All right, so again, the way we're going to find those is to look under second list, okay, or second stat, which is list and then draw my calculator with number 7 residuals. So I want you to do that on your calculator as well. Find those residuals. So you're going to get out of this, and you're going to go find your residuals and write them all down in a set, and then we'll talk about them. So pause the video and you do that. Now, when we analyze these residuals, you can see again that we have 4 negative ones and 4 positive ones. And the numbers are quite a bit larger this time than they were, but let's see what they mean to the context of our problem. In the context of our problem, we were looking at the average song size in megabytes and the approximate number of songs for a sample of a 32 gigabyte MP3 player. Okay, so in other words, one that can hold 8,000 songs had 3.6 gigs. Okay, so our numbers are a lot larger in this problem because we have these numbers for our Y values over here in our second list. And so we can't really say, well, these residuals are so much bigger because there's so much more air, but there is more air. And the way we know there's more air is because when we examine that scatter plot, we see that the little dots are further away from the curve. And that's just because maybe this isn't set up so much to be a power function. Maybe somebody's using the impression that it's a power function, that type of thing. Anyway, what we might want to write about this would be something like the residuals have relatively high magnitude. And magnitude means size, right? Which indicates that there's a large amount of residuals, so there's a large amount of error. So if there's a large amount of error, this would indicate a better model. Might exist. We don't know for sure until we go out there and look for other models or run different kinds of regressions and look at the error again. You might say something like the exponent, which was approximately negative 0.8315, is not as close. So to negative 1, we would like to have x to the negative first power as I'm analyzing this, so as I would like to see in a power regression. Does that mean that that our model is completely bogus and we can't use it? No, we can still make predictions off the model. It may not be as accurate as if more points were closer to the curve, but we can still make predictions off of it. So about 10,000 songs would correspond to what average song size? About 10,000 songs. So again, we have to ask ourselves, is the song 10,000 songs an X value or a Y value? And in this case, it's a Y value, isn't it? It's when Y is equal to 10,000. Okay, so I'm going to go to my window and see if I can have Y of 10,000. I can't. So I'm going to expand this. I'll go to 11,000. And that ought to be enough, don't you think? Oh, I forgot to put the Y equals on there. Y equals 10,000 in my Y equals. Oh, the problem is, I guess I need some more room on the left-hand side, don't I? Okay, so my window is set up to go from 3.38 to 6.02. Let's just set it to go from 0. You can't have less than 0 songs or 0 megabytes. And so my point of intersection is at about 2.945. So this would be about 2 point, and we might want to do it to the nearest tenth. So a 2.945 megabytes would really be about 3.0. Oops. megabytes, MB, MB. Okay, so we had to fix both the X and the Y to accommodate for that particular window. The average song size is 5.5 megabytes. That would allow approximately how many songs on a 32 gig player? So our last question is asking us about an X value. We type in the X value and we go to 5.5. It says you should be able to get approximately 5,900, I'd say 49 songs on there. It's not unreasonable to say you could get a part of a song, but probably wouldn't make any sense. So we're going to go with about 5,549 songs altogether. Okay, so that's really all there is to this lesson. When you get to class tomorrow, we will work on some problems out of the book, and there'll be those inverse variations again, and then the power regression, yet another type of regression that you can do for another type of curve that you can fit to some data. If you have any questions, please come and see me.